I guess not AI generated, I don't think. Sorry? I think maybe a year ago. Because I think I used it last year in class.
We're now down to 3 Raptor engines. We can see those trucks.
Quite a feat, I think. Our guy Elon, I guess. So does it stay on here? 13th of October 2024, down here. So yeah, so not so long ago. Quite an amazing feat, I would say. That was eye candy. I'm going to put this on again because this is related to, I guess. Starship is kind of related to what we'll talk about today in terms of powering such flight. And this is annoying. Bit of metal, I suppose, or something. Sounds like perhaps not very mild metal, I suppose. So we'll talk about conservation of energy today. It's a bit similar to conservation of momentum, as we've talked about before. But I guess the extra thing that we'll deal with is the ability to maybe include energy losses in the system, which we haven't done so far, but also to be able to accommodate the behavior of something like a turbine, gas turbine. So they're used in lots of areas. We've seen them used in some way on the tarmac of SFO, blowing trucks off into the wash. But they're a ubiquitous component of energy infrastructure, either in generating electricity from coal-fired power plants and nuclear power plants where you boil water, you pressurize water, and then you flash it through this, and it expands and changes phase from liquid to steam. Likewise, in geothermal fields where you get hot water out of the ground under pressure, and you flash it through a turbine like this to be able to generate electricity. So the expansion creates this rotational power, and you convert that by coupling it with rotating a coil inside some magnets to be able to generate electricity. So it's kind of a ubiquitous feature of our lives, even though we never see it, but all of our lives essentially run on energy. So that's what we'll deal with today. And so maybe take a track and talk about big picture things, which we don't often do. And those big picture things, if I can find them, would be here. A presentation. I won't show all of it. This is a presentation looking at actually storage of hydrogen, but it has some things in here that are useful to us. And this was a group of their EMS students, Katie Strass, Jen Holzhauser, Amisha, and Lara Owens, in Reykjavik, Iceland's first and then only hydrogen station, supplied with bottled hydrogen, with the idea that an island abundant in geothermal energy and hydropower, no coal, no fossil fuel, indigenous fossil fuels, would use hydrogen generated from electrolysis of water, splitting it into hydrogen and oxygen, and then use that to power their fishing fleet and to power their transportation system. I have no idea whether that took off. You can see when this was. It's 22 years ago. So I don't know exactly where that went to. But ubiquitously, I think this is kind of an interesting slide. It's put together by Gapfinder. Does it have a? I guess it doesn't have a tag on it. But it looks at the two axes are income per person on the bottom, which is salaries. Income per person is just GDP divided by the number of people. And the vertical axis in this is CO2 emissions per person. So they're both normalized per person. And so I'm going to go back. And this one is energy use per person. And it just makes the case these blobs are proportional in size to populations, colors are continents, and moving up to top right means you have a higher salary, and that is often equated in our society as a higher standard of living and higher happiness. It's not gross domestic happiness that they use in Bhutan, I think, right, to govern their lives. So the first one is in terms of energy use per capita. Everything moves up towards the top right. And then the second one, when it switches off, it's through the ages. So this is coming up to 2007. Now it's going to switch to the vertical axis being carbon emissions per person. And really, I guess it makes the point that currently most of our energy is fossil fuels with carbon attached to it. And so this graph also creeps up in the same fashion as the earnings per capita, energy use per capita does as well, because most of our energy is carbon-based. And you see different countries maturing, China especially, racing up to the top with a big population and its orientation along there. Global. And so sometimes it's useful to look at these in so-called Sankey charts. And Sankey charts just talk about energy use from cradle to grave, I guess, from its initiation, mind, and then utilization, and its ultimate disposition. And I guess we live on a planet which is something like 10 or 15 terawatts capacity, generating capacity. That works out, if you take that into energy use per year, into something like 500 exajoules, or 500 quads, which are quadrillion BTU, or 500 trillion cubic feet of natural gas. 500 through 1. The US uses about a fifth of that, so 20% of the energy use with maybe 5% of the population, less than 5%, right? 300 million. I don't think we're 6 billion anymore, right? We're much bigger than that on the world. And this Sankey chart would be pretty similar to other countries as well. And if you look at this, you see that the main use here is fossil fuels, petroleum, biomass, coal, and natural gas. And renewables being small, solar at the top. I can't even read these. It's in miniature view, presenter view, so I can't read it. These are all renewables. Nuclear would be in there as well. And so the 2 points that I guess that stick out of this are that if you want to make less carbon, then you can burn less fossil fuels. So inexorably, the switch is to more renewables and more use of gas instead of coal, which is lower carbon loading. And you can look at the ways that you do that. You can sequester carbon underground. You can switch from petroleum and coal to natural gas, which has lower use, or you could switch to nuclear, which has much lower carbon loading. And so those are the things that you can do to reduce carbon use. But the other astounding thing is that if you look at the rejected heat, stuff that isn't usefully used, the heat from your car, for instance, isn't being usefully used to get you from A to B, then something like, is it 60%? I can't quite see it here. 63% roughly. I think these are actually in quadrillion BTU. And for the US, as I say, they sum up to about 100 quads per year of energy use. And so these are the numbers here. And the only something like 33% of that is used usefully. So one way to have less carbon loading is to have more efficient engines and smaller cars perhaps as well. And the other one is to switch fuels and modes of generation. And so this is also a Sankey chart. The first one was 2018. This one is 2022. And this gives the changes in these, not changing very much. So the change in energy for, this would be solar, contributes 1% more to the grid at a loss in petroleum and coal of 3% and 1%. Natural gas has gone up because it's much cheaper to build power stations that are powered by natural gas with basically a gas turbine in it, just as we looked at now, rather than a coal plant which boils water and pushes it through turbines. And so a 1% change in here is actually, I think, from a doubling of solar maybe in those 4 years. So a big change in solar and wind only makes a small dent for now because it's such a small proportion, but presumably that'll get larger. So that's don't want to talk about that. I'm just making the point that conservation versus and worry about carbon depends on the administration. I mean, the facts of climate change are the facts, but whether you deal with it for livelihoods is it seems a political issue. And so the other thing is, you might have seen this before, this is the rise in carbon generation. So this is the rate of in gigatons of carbon per year. And it starts off about 7 in about 2004 or something when this paper was written. And it was just to give an idea of what you have to do to be able to reduce it from this trajectory which we're on, and still are on. Apparently in 2023 we're still on this trajectory, to get it down to be flat. And you have to do something for each of these so-called stabilization wedges. So this is 7 gigatons of carbon avoided over 50 years. So each one of these small slithers, these wedges, is 50 years times half a gigaton per year, right? The area of the triangle is 50 by, this is 1 on this side, so it's half is the average. So it's 25 gigatons of carbon avoided. And to get there, you have to do things like, geez, I don't know what that is to take, replace 800 gigawatts of conventional generation. So 800 big power stations off and replace them with nuclear power, or 800 power stations and replace it with geothermal energy or hydroelectric power, etc. And so those are the things that have to be done to do that. And so we'll talk about that today. So that's kind of the big picture where we come in. And I guess actually before I do that, I shouldn't have closed that so quickly because I wanted to make the point, is that all of these in the Sankey chart that we looked at, all of these generation capabilities are all driven by, many are driven by turbines, right? So hydroelectric power would be like a Pelton wheel or a Francis turbine with water going through it. Coal would be heating water and then passing that steam, flashing it through a turbine. Natural gas would be burning the natural gas directly in the turbine. And geothermal would be putting hot water in the turbine that flashes to steam, expands, and drives the turbine as well. So that's our task for today, is to talk about conservation of energy to be able to solve problems like that. So it's kind of where fluid mechanics meets thermodynamics in some respects. And many of you, I guess, will be taking Nelson's class as we speak, perhaps after this class, yeah? So that's what we'll do today. So, do we want to recap? We recapped pretty well last time, but let's do it. I added an extra page above this just because I could, and I want to use it. So what do we want to do? All right. The recap is that we remember that we took talked about Reynolds transport theorem. Oops, that's not. And we looked at these quantities. And in week 6, I guess, it was conservation of mass. Mass over mass was 1. And the conservation equation we ended up getting out of it was something like volume, rate of change times density, plus volume times rate of change of density, plus sum of mass rate equals 0. So that was for conservation of mass. Last week, we looked at conservation of momentum. V for velocity, lowercase v. So mv over m equals v. And you remember that we put these terms into this expression and we ended up getting, this is our value of b, so that was our particular component which was B. And we ended up getting a relationship which was something like sum of forces, which is a vector, is equal to sum of velocities times mass flow rates. These were, we looked at in all kinds of different ways, static velocities. And I guess we also multiplied that through by a radius on each side. Should put it before. And then this gave us a torque. And we also used that to, for instance, realize that force times velocity is equal to work, uppercase W, I guess power rather, rate of doing work. And we also had it that torque times rotational velocity is also equal to work. And this suggests that W is equal to Vs over R. These two are directly consistent with each other. They're exactly the same equation. This just has a lever arm in it from both sides for multiplying by R, but so that the energy coming out of it is exactly the same. And so what we'll do today is we'll talk about conservation of energy. And the term that we will use is mass times energy. Energy per unit mass. And if we do that, then ME over M is equal to just E. And we'll write out what energy is. And so energy is just equal to, what we're going to do, I'm not going to do it, but what we would do is we would substitute that into here as B and B and uppercase B. We won't do that, we'll just come out with the expression. And the expression would be, in the terminology we'll use, is the book uses U with an inverted caret on it, I guess. Pressure over density. Velocity squared over 2 plus gravitational acceleration times elevation. And these first two terms are collectively enthalpy. And their units would be joules per kilogram. We said that this energy is in energy per unit mass. Energy is joules, Newton meters, per unit mass is kilograms. And so that's kind of strange because we have this term, these all have to be the same units, but V squared over 2 is just meters squared per second squared, right? So the units for this would be meters per second times meters per second, which doesn't look like this. But if you multiply top and bottom by kilograms, and you look at gathering terms, a kilogram meter per second squared is a Newton by definition, right? 1 Newton is the force required to give a kilogram an acceleration of 1 meter per second squared. A Newton times a meter is a Newton meter, which is a joule. And a joule per kilogram is exactly what this is, right? So this strange thing that looks like meters squared per second squared is actually can be generated into something which is joules per kilogram, which we've just done. And so these all have to be added together, and they represent, as you can imagine, joule per kilogram is just energy per unit mass. And so what we can do with this is realize what we've done, and you could recognize this. This is the velocity squared term in Bernoulli. This is the elevation term in Bernoulli. This is the pressure head term in Bernoulli. All we've added to it is something which represents the internal energy of, say, a hot fluid before you flash it to steam, to be able to accommodate that in basically Bernoulli's equation. If we substitute this E into Reynolds transport theorem, that's what you end up with here. And we won't worry about that derivation, but we will use the two results that come out of it. And these are the two results that come out of it. The one we've just derived is this. Well, kind of derived. If you substitute E into Reynolds transport theorem above and play around with it, you'll end up with this. And you'll recognize this, right? This is Bernoulli's equation. So you could think about this being along a streamline. We'll only deal with it in this one-dimensional form. Mass flow rate is what I've called uppercase m in the past, but let's call it lowercase m here. M dot equals m dot. And like a streamline velocity, it only has magnitude, is always positive, and it goes from upstream to downstream. It's important now in this that we do upstream and downstream. Before it didn't matter because there were no energy losses in the system. And that we can either put heat work into the system, Q dot net in. So this is positive if it's going into the system. Or we can put work into the system, W uppercase net in. And so these are those two terms. So W net in would be putting a pump in this circuit to be able to push water from upstream to downstream. And having it water run through here and turn a turbine would be to take energy out of the system, which would be net the negative value of this. So I guess we should probably also mention that W dot positive is a pump and negative is a turbine. Mass rate is always positive and it's always out of the system. We don't have the sign conventions we had for our multi-dimensional conservation systems for, like, as in last week. These would be what we have called, in would be 0.1 and 0.2, right, in this parlance, just done in this way. And all it does is it has the pressure term, the pressure head term, included in with this enthalpy. And so H dot is just equal to internal energy per unit mass plus pressure over density, P over rho, which is what we had up here, right? This term here. And yeah, and that's it. So let's deal with that one now with a simple example. There's one in these notes, and I'll just use that. And so what we'd like to be able to do is to be able to calculate how much work we get out of the system. If it's a turbine, for instance, if fluid, it's just like a streamline. I guess I hesitate doing this because this is also, these have to be equivalent to each other because it's a steady state system. So these are equivalent to each other. So it's just like a streamline velocity. Actually, streamline velocities aren't equivalent to each other. These mass rates across these boundaries have to be the same, I guess, because of velocity, density, area in equals velocity, density, area out. Steady state, OUT. And then the final two relationships which are important to us are the work that we get out of the system is equal to this. I'll write another one, which is the pump head in units of length is equal to the work rate. So work is energy times rate is power, divided by, I guess it's volumetric flow rate times unit weight, which is equal to volumetric flow rate is, this is rho g, and so this is also mass rate times g. And so this, I won't talk about this now, but this will also cast this one-dimensional streamline equation that has this important enthalpy term which we want to deal with. We can also write it as Bernoulli's equation with energy, equivalent energy put into the system and also losses in the system. But we won't do that right now. So let's use this. There's an example that I took out of the book, which is in these notes, which I'll run down. We'll come back to this page if you haven't, and it'll be recorded if you don't have it. Saved you all of this. Oh, God, I'm so generous. Don't want to do that. Simple example. So, turbine. So the idea is that steam goes in to one end. So this would be what we would term mass flow rate. Also has to be the same mass flow rate going out. Steam enters the turbine, comes in at a velocity, and with an enthalpy of, so it's 30 meters a second, enthalpy of 3,348 kilojoules per kilogram. So this is energy per unit mass. Steam leaves the turbine as a mixture of vapor and liquid, having a different velocity and different enthalpy. So if the flow through the turbine is adiabatic, so this means that bad Q is equal to 0. There's no heat exchange in the system. Then we just have to be able to calculate the work output per unit mass. And so the work output per unit mass is, even though I didn't stop to do it, is this. So total work out of that system, that turbine, divided by mass rate, and this is the total work per unit mass, which we'll use. So what we could do is we can use our expression, which is written out here. You'll recognize this. Enthalpy, so it matters between doing in and out. So number 2 is out, and number 1 is in. These are what we called in and out before. This is enthalpy, this is velocity, this is elevation. If we take a datum as z equals 0 and have a line through here, then z2 equals z1, right, by definition. So that term drops out. It's adiabatic, so we lose that term. We have the work out of the system as a result of these two different inflows. We have a mass rate in, which we can calculate. And we have everything else we need. We could usefully divide both sides of this by m dot. And this becomes our lowercase w, right? Lowercase w, which is work per unit mass in the system, which is all we've done here. And the only two terms that we have left are these two ones red underlined. We know the enthalpy going in. We don't need to know the mass because we just eliminated it by dividing m dot by m dot, because we're getting the output per unit mass input, and that's not one of the things that they gave you anyway. And you just have to look at the values that were given for enthalpy and for velocity. And so you have each of those. So inlet enthalpy is 3348. Outlet is less. It's lost enthalpy in changing phase, presumably, and coming out, going in as steam and going in as a high-pressured liquid and coming out as steam and vapor. And we have a velocity going in as well. So we have V1 and V2. So you substitute those. We already did the example that V squared over 2 in terms of units is just equal to meters per second. Forget the 2. And we can take those as kilograms per kilogram. Then we can do exactly the same as we did before. And we get kilogram meters per second squared. Not joules, that's a Newton, right? This is a meter. So together, these two are equal to a Newton meter. And this is a kilogram. So this is joules per kilogram. And this is just the math. And so everything you see here, I'm not going to go through it, is the conversion to get from meters per second squared, all squared, to get to kilograms per joule. You just have to, and to get from joules to kilojoules by doing standard conversions. I'm not very good at that, so I'll just sidestep that. But the whole reason for doing that is just this conversion, because you have this is written in joules per kilogram, and this is written in meters squared per second squared. And so you just have to multiply it by kilograms, top and bottom, to get it in joules per kilogram. You're not changing the units because you're just multiplying by 1, right? And just manipulation to get the rest. And it gives you the amount of work that comes out of the system in kilojoules per kilogram. So that's, so that's the work. So that's in meters per second, so in joules per kilogram rather than joules per second. So it's not power. Okay. So that's why we would want to use that expression, which all of a sudden now we're able to get chemical energy, I guess it could be as well, right? If you're burning a fuel in a jet engine, you're burning jet fuel, which is kerosene, then that gives you, this reaction gives you the fuel energy, the internal energy of the fuel is liberated, and it's creating a jet which comes out of the system, which drives the engine. Okay? So we will use that sparingly. The equation we'll use much more is the one that's written next to it. Actually, we could also write this equation as do I want to do it? Yeah, I'm going to do it. Dot. So if we wrote it in terms of H, if I split terms up to take the the influent terms onto the right-hand side, we'd get this. That's out plus GZ out is equal to Q dot plus W dot work, thermal energy plus mechanical work plus M dot H in plus a half V in squared plus GZ. I could divide through both sides by G, I guess, if I wanted to, and you'd instantly recognize Bernoulli. So this is the elevation term, If I divided through by G, it would be elevation head. This is the velocity squared inertial term. This includes both internal energy plus pressure. If I divide this by G, then this is unit weight, our pressure head term. And this is now, this would be our downstream location, and this would be our upstream location. And so I do that because now that the expression that we'll look at is we'll use this term above it, which is written exactly as this. And so if we don't want to use the enthalpy term, and we're not too worried about thermal energy into the system either, then we can write this expression along a streamline as the equation above it. And I'll write it out as it is here, just as in, it's actually in, I'm going to write it as P2 over unit weight plus V2 squared over 2G plus Z2 plus HL equals the same terms on the other side. The pressure head upstream plus the velocity head upstream plus the elevation head upstream plus the so-called pump head. So this is got just by putting exactly this expression E back into Reynolds transport theorem, no different from what we've done before, but just manipulating it in a slightly different way to give us terms which neglect this heat rate into the system. We're assuming it's adiabatic, and allowing us to write this work term in terms of two heads. And the two heads that we deal with are pump head, which is if we add energy into the system to pump water from upstream to downstream, and a head loss term, which accounts for frictional losses in our system. And the easiest way to illustrate this equation, for some reason it's kind of backwards. Let's flip it the other way. I won't rewrite it. But if we look at it in terms of physically what it looks like, graphically what it would look like, is it would look like this. We have a pipe that is carrying water downstream, which is these two lines close together. It's, I'm going to go gray. And in this pipe, I'm going to have a pump. And let's look at the individual components of this. So this is Z equals 0. This is location 2. And this is location 1. Then this would be, you know it, Z1. This would be Z2. They don't necessarily have to be the same. This would be P1 over gamma. By definition, well, actually, let's see if we can rationalize it. This would be P2 over gamma. This would be V1 squared over 2G. This would be V2 squared over 2G. And the last remaining component would be HP and HL. Okay. So that's this expression written out in graphical form. The left and the right hand sides have to equal each other. So these bars have, this has to be a horizontal line. This is referred to as the hydraulic grade line. This is the energy grade line, EGL. This one underneath it, grade line. Don't think my writing's getting much better. And so this line up to this point here is Bernoulli, as you've previously known. That's the graphical expression of Bernoulli. It hasn't had this pump in it, hasn't had this line here, and it hasn't had head losses in the system. So now what we've done is we've added two components. We should note that HP is positive if a pump, negative if a turbine. These velocities are always along a streamline, so they're always positive, right? Pressures are whatever they are, and elevations are whatever they are. But these velocities are always along a streamline. This is a streamline, yeah. The streamline for this particular system would be through this stream tube. So I guess this would be V1, V2, and this would be V1. If the areas were constant at each end, then V1 would equal V2, and so these heights would be the same as well. Since this would, in Bernoulli's equation, would be horizontal, that means that the pressure drop between upstream and downstream, if this didn't constrict, is 0. So you're driving flow, but providing no pressure needed, no pressure loss to it. It's a it's a perpetual motion machine, right? It's requiring no energy. And so it just keeps on running. But now we're adding two other terms. One is that we have a head loss. And so the head loss just accounts for frictional losses in the pipe. So you know that if you drive flow, and I won't complicate it by drawing a little circle to take it out, but if you drive flow down a pipe, we've always assumed that the distribution of velocities will look like this in the pipe, if I can draw it. But actually, what happens really is that viscosity requires that the velocity at the wall sticks the velocity to 0 at the wall. So the velocity profile in a real pipe is parabolic, actually, across the thing. So this where viscosity is not equal to 0. This is where viscosity is 0. This is Bernoulli. This is Bernoulli plus these two terms. So this friction is just a shear stress that's applied on here, which we've already met, right? We know that frictional shear stress is equal to viscosity times the rate of change of velocity with r as you go across here, right? So if this is the radius of the pipe, then this gradient here says how much energy is taken up in this, and that's what's manifest in this term here. And so just to make the point, if you flow one way or the other, it's the same as I used to drag my bag across the table. And so to pull the bag across, I've got to apply a force. If I want to get it back to this point again, I have to provide the same force to get it back. And so friction always acts against motion. So HL will always be positive. This will always be positive. And the pump head that we put into the system, and we said that pump head is equal to what? This is the equation we'll use all the time, is equal to the power, the rate of doing work divided by volumetric flow rate and unit weight of the fluid, which is the same as the bottom can also be written as mass flow rate times G. And so we can use that to be able to calculate some simple things, right? So that's about as simply, I guess, as I can make it. How are we doing for time? We've got 10 minutes. Do an example. It's a neat example, I think. I didn't really talk about pump storage, but one of the things in the new energy grid is that if you use renewables, you get wind power when the wind blows or when the sun shines, and you want it all the time. You want so-called dispatchable energy. You want to be able to create it by spinning up a turbine, and that if you only make it when the sun shines and when the wind blows, you have to store it somehow. And so there are different ways to store it. Making hydrogen is one way, and storing it underground. Using pump storage schemes also is another one. There's actually one in Pennsylvania, in northern Pennsylvania. I don't recall what it's called. But the idea is that at night time, when electricity is cheap, you pump water into the top reservoir, and then when you need it, when everyone turns their toasters on, in the morning, then you run it back through and generate power, and that's the diurnal cycle, to be able to basically change it into potential energy, which is stored here, and then to put it through kinetic energy to run a pump, and then use electrical energy to be able to repump it back to the top. And so we can apply what we've known so far. I don't really like green. I'm going to change it to be able to represent that. So we can write our new Bernoulli equation for this. And so if we do that, it matters where we write it from. So let's do it from 1 to 2. I'll do it horizontally here. So this is our stream tube, and it has in the middle of it HP. And so we can write it as Z1 plus P1 over gamma plus V1 squared over 2G plus HP is equal to Z2 plus P2 over gamma plus V2 squared over 2G plus head loss. And so we can get rid of a whole bunch of these terms, right? The big tank assumption means that the velocity, if we take our points on the surface of this at A and B, this could be 1 and 2, or it could be 2 and 1. We'll switch them around because we want to have flows in both directions. And so the big tank assumption means that this is 0. The atmospheric pressure assumption means that this is 0. And that means that we're left with HP. I think that's how I want to write it. Yeah. HP is equal to Z2 minus Z1 plus HL. So that's our basic equation that we'll want to use. And so we could write it in terms of letting it flow through the turbine from top to bottom. So flowing downhill. So we'll still use this equation. HP is equal to Z2 minus Z1 plus HL. HL is always positive, right? We've said we don't know what it is. We don't care what it is, but we should be able to get it. We'll talk about ways to get it somehow. In this case, Z2 is less than Z1. So in this case, this will be negative. So if there are no losses in our system is perfect. Let's say HL equals 0, perfect system. Then we'll get this amount of energy out of the system, this amount of head, which is going to be negative. Negative means it's a turbine. We're generating power. So a negative value of HP means we're generating this head. And if we wanted to convert this head into power, we just use Q unit weight. Water is flowing. We don't know the volumetric flow rate. We have to do something else to calculate that. And if we know what this pump head is, we could calculate exactly what that is from this head. The bigger the head, the bigger the power that you'll get out of it, obviously, because of this. And you can see that that amount of power that you get out of it will be lessened by adding a positive value of this to a negative number. So it'll be reduced by the friction in the system, which you'd expect. If you write the equation in the opposite way, that we go from 1 to 2, still this relationship, HP is equal to Z2 minus Z1 plus head loss. Again, this is positive. But now Z2 is larger than Z1, so this term here is going to be positive. And so this means that a positive value is equal to a pump. So now it gives us the power that we have to apply to be able to pump it uphill. If head losses in the system were 0, then the amount of energy you get by flowing it downhill for the same volume of water would be exactly the same amount of energy you'd have to consume in getting it up. It's a perfect machine. And so then all we've done is added an energy term into the system, into Bernoulli. But if we have head losses, which we say that we might do, then it means that you'll never get back the same amount of energy by pumping it up, and indeed you'll lose a certain amount of energy in it coming down. So you lose both ways. You have to provide more energy against friction to get it up, and friction will diminish the amount of power you get out of it as it passes through the system. So you lose both ways. So that's it. So 2 ways of looking at energy, always in a stream tube. Mass flow rates, we don't have to worry about the conversions of across boundaries and stuff. They're always positive. Velocities are always streamlined velocities, so they're always positive. And it includes these terms that represent either, in this equation, energy taken out. This is our W dot term, energy taken out of the system in shaft work and losses in the system. And in the other equation, it allows us to take in chemical energy or phase change energy in terms of enthalpy to be able to also calculate the behavior between upstream and downstream. That's it. And so the other thing that I guess this is indicative of, now that since we've written Bernoulli, did I write it down? I guess I did. Since now we've written Bernoulli with these head losses, these are actually the things that contribute to the head losses you flow through porous media. And so the whole issue of porous media is that if you pump water out of a well, in addition to the energy you have to do to raise it up to the ground surface, you have to pump it from the sides. And flowing horizontally, Bernoulli would tell you if you just suck, it'll just come straight away for no energy expended. But the reality is the pressure at the outside and the pressure drawdown at the well gives you a gradient in pressure drop. And it's that pressure drop over a length which is working against the friction in the pore space to be able to do it. So this way is, we talked in one of our classes about Darcy's law. The velocity at which fluid flows is equal to a hydraulic conductivity times a drop in head, or a velocity is equal to a permeability over viscosity multiplied by a change in pressure with length. These energy drops are manifest because pushing it through a porous medium, just like pushing it through a pipe in a house, takes some energy because of this friction on the pipes. Because of this. There's some frictional resistance in the pore space, and the velocity profile within a pore, within a porous medium, would be a bit like this, and it'd be dragging on the side of the pores. That's it. So we'll talk about how this fits into other views of how we'll do some examples, I think, next time on Wednesday to cement these concepts. We'll almost always use the form that we just looked at now, which is this, rather than the enthalpy one, just because of the nature of this course. But this is how fluid mechanics and thermodynamics fit together, in that we've basically defined the first law of thermodynamics, that energy is neither created or destroyed, but merely changes its form, and that's what it is included in this. Great. Thanks for coming out. We had a big class today, rainy weather.